HVAC 360 is brought to you today by VR Systems. Working from home a bit more than usual? Are your only pedometer steps between your desk and the fridge? Tracksuit feeling too tight? Well, maybe it's time for our new product, the Virtual Snack Machine. Feast to your heart's content and never have to go to the grocery store again. Our patent-pending combination desktop device and glasses will not only display any food of your choosing, but will replicate the sound while you eat and produce a matching aroma using the finest essential oils on the market. You'll never have to share that bowl of candy again or guess whether your visitors have washed their hands lately. Order now. Operators are standing by. Hey everybody, welcome back. Matt Nelson here, your host for HVAC 360, helping you be the best and the brightest in the field of HVAC. I do that either by sharing information, specific lessons learned from the field, or talking with industry experts. And if all this information leaves you a little bit hungry, you can sign up for my weekly newsletter, or subscribe to my YouTube channel. All right, so what's up for this week? This week, again, I am dishing out some of the highlights from a session that I attended at the ASHRAE conference in Orlando in the beginning of February. This one is, I guess what interested me about this one is it evaluates systems that are being retrofitted into existing buildings. The benefit of this session was, I guess, twofold. One being I get to learn some lessons learned from some actual projects from retrofits, and the other one was the thought process behind how engineers determined what were the best systems to put into buildings. I mean, when you're analyzing the system, it's one thing. I mean, usually commissioning authorities will get a set of drawings and it's already pre-laid out for you. But it always kind of fascinated me about understanding what the process was between the owner's inception and what can be retrofitted into a particular project, and how do you rank those things? So that's something that I've always kind of looked for a little bit more insight in. Again, these are my takeaways, interpretations I wanted to share with you, and really only the fraction of the information, and it may differ slightly from each session I heard, as it's just what I wrote down. So I tried to put it through the truth machine and make sure that it smells okay for common distribution. But if you want to read about the half the presentation, I actually did find it on the CSE magazine website, so I will put a link to that in the show notes. All right, the first half of the presentation was focused on Marston Hall. Marston Hall was a classic engineer building built back in 1903 at Iowa State University. Now, that is pretty much what you're thinking of in a 1903 engineering building at a state university. That's exactly how this thing looks. Fun fact of the day was that the engineer on the project actually had attended classes in that building 20 years earlier. If you can imagine, the building was built with just heating and ventilating in mind. So the mechanical spaces and the mechanical chases were obviously limited. You can imagine high ceilings, a central corridor. Most of the things had operable windows on the outside. And as always, the case for this type of building was that they needed to preserve the building's architectural integrity. That's always the case with these retrofits. A lot of times you can't. There's only so much you can change about them. But when it's an architectural piece like this is, there's really stringent limitations put on your design. All right, so some of the design parameters that they had were they were going to have 44-degree chilled water and 90 psi steam being supplied from the unit, being supplied to the building from a central plant loop. Now, so that meant that they didn't really have to go through any sort of plant. They didn't have to put a plant in there as far as like a boiler plant, heating plant, or a chilled water plant. So that was good. They saved some space there. They actually did some enclosure improvements. Obviously, as you can imagine, they pretty much had just mass walls and single pane windows. Those were changed out. They added wall insulation and some double pane windows, which were still operable. And also, regardless of what system was chosen of the four, they were going to have demand control ventilation and retrofit the building with LED lights that was combined with vacancy sensors. So now onto the systems. They had four systems. First one was kind of your standard central air handling unit with VAV. The second one was fan coil units with a DOAS unit, dedicated outside air. They had the VRF, the variable refrigerant system, with the DOAS. Or they were going to have chilled beam / radiant heat with a DOAS. Now, obviously, the central air handling unit with VAV, retrofitting that into a building that was this age was very, very difficult. Because of the amount of outside air they had to push around. Usually, when you end up pushing air around, you're going to need some extra space, and that's one thing they were short of in this particular building. So, too large, too much space, and the fact that the DOAS was much smaller and it fit into the basement, which was where the air handler, the old air handler, used to be. Was kind of a benefit. So they were looking at one of the three with the DOAS system. So, and they basically, all four systems, and I guess some of the methodology behind evaluating these four systems, they kind of developed a pros and cons. Not kind of. They did develop a pros and cons list. That actually, if you go to the magazine article, you can see what those actual pros and cons were. I'm going to list them in short here, but if you want to kind of see what their process was, it's spelled out a little bit more in that article. Now, for the fan coil units, so everything's got a DOAS, so we'll kind of eliminate that from consideration. The first one is going to be fan coil units. Obviously, having a 4-pipe fan coil unit and multiple spaces around the building, you're going to have a lot of maintenance points around the building, filter changes. They're going to be noisy with the fans, relatively speaking, to both the other issues, or both the other systems with the VRF and chilled beam. Those are going to be quieter. And you're going to have condensate because you are dehumidifying at the fan coil. Maybe not entirely, but you're going to have to do some dehumidification there. So that was part of that issue. VRF, one of the things, the pros and cons there, maintenance. Actually, most of these are the cons I'm listing. The VRF had the maintenance, again, with multiple points. They had compressors. Even though they were quieter in general, they're going to have compressors, they're going to have filters, kind of some of the similar things that you would have with the fan coil units. Heating would be an issue, and also you'd still have the condensate. Lastly, the chilled beam with radiant heat. The problem there is the Can I say this right? The humidification control. Oh boy. The humidification control. So when you had operable windows, like they had changed out, they went from single pane to double pane, but they were all operable. That's one of the things that they're going to have to figure into the chilled beam. Now, I guess when push came to shove, they elected to go with the chilled beam. Now, I would say chilled beam throughout the building. There were a couple different exceptions. They did end up using fan coil units in the corridors and vestibules. That was pretty much straightforward there because of the active heat load that they needed in Iowa. And they had a large auditorium, and for that they used underfloor air displacement system. So that was kind of a different system in and of itself as well. What were the lessons learned that they took from this building? So I guess the low amount of outside air for the chilled beam system means that the duct sealing was especially critical. One thing they found is that, typically you're going to have contractors doing a great job about sealing ductwork. Especially if you call it out properly, they'll usually do a good job there. But what they found is the VAV boxes were in fact points that would leak a lot more. And that's really critical when you have a certain amount of outside air and you trying to get it directly to the space. Any sort of leakage is going to eat away at those, at the quality of the system that you're installing. Another one was they had chill beams. Again, a certain amount of airflow is needed to create a cooling effect. So that's the activation airflow. So low outside air means that they needed a parallel VAV box to be installed. So it wasn't just any VAV boxes that we're talking about. They were parallel VAV boxes. So this would actually add the necessary airflow during the cooling seasons that would allow the chilled beam to operate properly. Now, understand that, unlike the fan coil unit, which is going to be, whether it's heating or cooling, and it's going to run year round, at least for the parallel for the chilled beam system, they only needed that parallel VAV fan just for the heating season, or just for the cooling season, rather. During the heating season, they could shut it off, and they would just blow the dedicated outside air, into the chilled beam, and it would be distributed into the room. One thing that they pointed out is that choosing this system may require you to have the DOAS running 24/7. That may be necessary from time to time to control indoor humidity. So that wasn't something that they could get away from. One of the things that they did talk about was the EUI. So I don't necessarily know if they selected the system based on EUI. It might be one of the factors. But just to kind of run down some of the numbers, real simple. Pre-renovation, they had 147, an EUI of 147 kilobTUs per square foot per year. So 147. The code minimum currently was 86. So that's the code minimum. Their design was 53, an EUI of 53. So that was much better than the code minimum. And then they discovered when they measured it, it was 75. So there was a little bit of a discrepancy between their design, which was 53, and the install, which was 75. Obviously, they're going to be doing an M&V. I guess not obviously. For this building, they're going to do an M&V. And that was part of the reason they were able to kind of identify some of the things that were going wrong. And what they found out was that the steam heat at the DOAS unit for the preheat coil was commanded open 100% of the time. So not only were you heating the air up, but you're also cooling it down to meet the discharge air temperature. So having fixed that and monitoring it, they ended up with an EUI of 58. So their design was 53. What they were coming back was 58. So it was just 10% higher, which is pretty good from what they calculated. So that was Marston Hall. Now the other building was for a school of architecture. Much fewer details for this one. This was a building that actually they had added on multiple times. So they started with a classic stone building that is similar to Marston Hall, and then they attached a workshop building that had monitor skylights, and that was kind of like an all wood structure. And then they added on to that. There was another building that they added on connected to this kind of architectural school. So they had probably like 3 or 4 buildings that were all connected together, so you could walk inside. So that needed to be changed. Their evaluation process was a little bit different. And I guess they had different categories. So if you imagine kind of what is it? 1, 2, 3, 4, 5. They had 5 different categories that they ranked using a bar chart, and they compared these systems to one another. It's a little prettier. One of the categories, the multiple categories they had energy efficiency, affordability, life expectancy, whether it is easily maintained, and controllability. So, I mean, if you looked at the pros and cons list over for Marston Hall, some of these things are also highlighted there. They're just not put in this kind of like this bar chart to evaluate, compare the pros and cons. So I guess, in looking at these 2 examples, I was left wanting more because as an engineer, I want more solid numbers. I want a score. Like this one got a 3.2 and the other one got a 3.4. But they put these rankings, these general rankings together for the systems, for those different categories, and they had a conversation. The thing is that it isn't always the most energy efficient that wins. There's a lot of different factors, as I pointed out with the multiple categories, and a lot of different people who care, really could care less about energy efficiency. Maintenance staff, they want it to be easily maintainable. They want the life expectancy to be good. Same with the, the people at the university. There's a lot of different things that everybody prioritizes these categories differently. So that is kind of how that worked out. So based on the scoring, the winner was a VAV with demand control ventilation. All right, not really exciting, but I think not only was the important point that there were people around the table that had different priorities than the engineers, maybe just looking at energy efficiency, but that if you get the right options with a standard system, you can really make that system energy efficient. It's just not, you're not going to get, you don't need the latest and greatest, to get the energy efficiency. You just need a well-designed standard system most of the time. And really that's the one that really, ticked all the boxes for the design team and the owner. So some of the lessons learned that they had for this project, one was beware of, services that feed through a space. In this case, there was a steam line that was feeding through the building. And again, this is kind of a meandering building. So obviously, there's a lot of things that that could go wrong. I've seen projects with gas lines in the way, electrical services, whether it's security, video security, or some different things that connect different parts of the campus. If it goes in a certain location, it might be in the way of putting a building up. So that's one thing that you need to be able to talk with the facilities people and get those responsible parties in the room, have a conversation. What needs to be done? How are we going to maintain it? What happens if something goes wrong? Another thing that happened during this particular renovation was during the demo, there was a little bit of confusion and maybe not spelled out so exactly as to what was to remain. The demo contractor cleared out the mechanical space. Unfortunately, they also cleared out a pneumatic station that fed other buildings. Okay, not so good. That needs to be saved. A lot of times, when you're dealing with pneumatic systems, even if it's a renovation, especially if it's a renovation, cutting lines and capping lines, and depending how things are controlled, which is not the easiest because that's not always spelled out. There's not a drawing, one-line drawing with the pneumatic system, generally speaking. So that's really hard. So if you have pneumatics in a building, take note that you're going to have to do something. You're going to have some process to cap it off or figure out how to isolate that. And they're going to have to understand, I've worked on a project where, for example, they did it floor by floor. and they renovated floor by floor, and each floor they had capped the pneumatics. Everything was fine until they did the first floor, and there was a basement yet to go. But the first floor, they capped the pneumatics, and they lost control of the stairwell heating system. So, that needed to be, changed and addressed. All right. Another lesson learned that they had, they found it very valuable to review the drawings during a page turning meeting. So that's just kind of where you sit down with everybody around the table, have all the parties involved, and you kind of go through the design. You point to things. You're like, okay, this is how it's going to go. Everybody's looking at the drawings. People can ask questions. You can point to things and just go through the set like that. So that really can be, they found that to be really invaluable. Another lesson learned, stick to your scope. A lot of times when you're doing a renovation, scope creep is all over the place. So stick to your scope and, you're going to be a lot happier. Proceed carefully and carry a big contingency. I guess from their standpoint is a big design contingency. Again, that kind of went with the first, the previous one where you stick to your scope. But if your scope creeps, carry a big enough contingency to be able to count for that. So there you have it. Those are my session notes this time. As always, some show notes and that link to the article can be found at hvac360.com/162. Well, thanks so much for taking the time and listening. I really do appreciate it. I hope this was helpful. I hope you learned something. If you know somebody who's looking to up their HVAC game, consider sharing this episode or another one of your favorites with them. This is by far the best thing you can do to help spread the word about the podcast, and I really do appreciate that. Other things you can do, subscribe, like I mentioned at the top of the show, at hvac360.com for a weekly dose of the written word, and browse on over to my YouTube channel and subscribe if video is more of your thing. Lastly, I'd be greatly honored if you would consider leaving me a 5-star rating and review over on Apple Podcasts, if that is your thing. All right, well, that's a wrap for this episode of HVAC 360. I'm Matt Nelson, helping you be the best and the brightest in the field of HVAC. And as always, know what you build and share what you know.